Welcome back. Now that we learned that two-dimensional LSI systems, in producing the processed image, they perform the convolution of the input to the system with the impulse response of the system, another 2D signal, we can start getting our feet wet by playing around in some sense with various LSI image processing systems for which we know their impulse response. So for example, if the impulse response of a 2D system is flat over, say, a 3x3 region, and flat means that each sample in the impulse response has the same value. So for the 3x3 example, each sample has value equal to 1/9. So in this case, what will the effect of such a system on an image going to be? We can write a simple program of a few lines to perform the convolution of the two images, and we can utilize any image we have available, so we can find out what this effect is going to be. We will see that the high frequency content of the image is reduced. The image will look blurry. The system with this 3x3 flat impulse response is a low-pass system or a low-pass filter. We will also see examples of systems which reduce the low frequency information in an image and allow the high frequencies to go through the system unchanged. In this case, the edges in the image at the output of the system are pronounced. Such systems are referred to as high-pass systems or high-pass filters. We will show such examples early on in the course so that we obtain a good feel about the manipulation or filtering of images. We jump the gun in some sense in this segment by providing image noise smoothing examples and the extraction of edges in an image, which is a topic that we will cover in week 5, and this is the topic of image enhancement. We actually also show an example of filtering impulsive noise, or more specifically the so-called salt and pepper noise, both with an LSI and a nonlinear filter, for demonstrating that LSI filters are not appropriate for removing such type of noise, while the nonlinear filter or the median filter specifically indeed is. So it's always fun looking at images, and let's proceed with the material of this segment. As we saw, in processing an image with a linear and shift invariant system, or in filtering the image as we typically refer to, we are performing the convolution of the image with the impulse response of the system. In doing so, we need to have information about the image outside its borders or boundaries, which is typically information we don't have, since in most cases the image is a windowed version of a larger scene, since we have a limited view of the larger scene through the camera lens or the sensor in general. So let's look at this specific example. You see here on the left a synthetic image. It has 200 by 200 pixels, and it's a binary image, and therefore each of these squares is 50 pixels wide and tall. We convolve this image with a 15 by 15 symmetric flat filter. So the impulse response of the filter is centered at 0, 0. The height of each sample of the impulse response is 1/255, so that if I sum up all the samples, the sum is equal to 1. Clearly, in finding a filtered value of the image, let's say at this location on the boundary, I bring the flipped around impulse response of the system at this location, right? And it's clear that I need here a band of width 7 columns for this particular filter of pixel values that I do not have, that do not belong to the image. So for this particular example, I need to know a band of width 7 around the image, these boundary values. You also see down here a line that goes through around here the image, so you see the black value 0, white values 255, and so on. I have various ways to generate this boundary information. The first way is zero padding, which means simply that I assume all the required boundary values are equal to 0. With the symmetric method, the size of the image is extended by mirror reflecting it around its borders, and with the circular method, the image is periodically extended. If I look at all the results here and the one-dimensional line, it's the line at the same location through all images shown down here, it's clear that away from the borders, the result is identical in all cases. This is actually how this pulse here is shown, looks like after I perform the convolution with this particular symmetric filter. So it becomes narrow up here, and then these sharp edges become smooth or become broader here, right? However, in all these 4 cases, it's clear that the resulting images differ depending on how these boundaries were generated. It should be clear that there is no method of choice here. There's no kind of clear winner telling us which way the boundaries should be generated. We show here an example of a color image on the left being processed by a system with impulse response shown down here. It's a symmetric impulse response, which means that this is the H00 value of the impulse response. It is called a low-pass filter because it allows the low spatial frequencies of the image to go through it while rejecting the high frequencies. Then these concepts will become clearer later in the course. But this manifests itself by looking, for example, at this part of the original image. You see the fine branches there in it, while it's harder to do so in the low-pass filter or blurred image. For this 3x3 filter, I need a boundary of width 1 around the image to process it and to use the symmetric method that we mentioned earlier. Finally, this is a color image, and in processing it, we process each of the 3 channels, the RGB channels, separately with the impulse response of the filter shown below. This is the same type of experiment as the previous one. You see the original image on the left, and the filtered one is shown on the right. The impulse response of the filter is different now. It's flat. It has support 5x5, and all the values are the same, 1/25. We see that with this filter, the blurring effect is more severe. In other words, more higher frequencies are rejected or attenuated as compared to the previous case. We show now the result of processing the same image with a filter with the impulse response shown down here. It's a symmetric filter, so this is the H00 value of the impulse response. And this now is a high-pass filter, which means that the low frequencies are attenuated or rejected, while the high spatial frequencies are allowed to go through the filter. And high spatial frequencies manifest themselves in regions of the image where we see large variation in intensity values, and these are the edges in the image. So this type of filter performs edge detection for the given image. One of the uses of low-pass filtering is to remove noise that might have been added, might be present in an image. So on the left, you see the same image you've been working with, to which noise has been added, IID Gaussian noise with peak signal-to-noise ratio around 25 dB. So this image is processed with the same filter that we used before. This is the H00 value of the impulse response, and on the right you see the processed image. Some of the noise has been removed, as hopefully somebody can see by looking at this image, while at the same time the price one pays is that the image is now blurred as compared to the original one. We'll talk about noise reduction and other enhancement techniques later in the course. Here is another example of noise filtering. You see on the left the image we've been working with, to which noise has been added, but this time the noise is not this Gaussian broadband noise, but instead is a type of noise we're referring to as salt and pepper, since it resembles throwing salt and pepper on the image. It's actually colored salt and pepper because the salt and pepper type of noise is added on the 3 channels separately and gives this colored appearance. So if we apply again the filter shown here to this image, that's the impulse response of the filter we've used multiple times before, you see the processed image on the right. So in this particular case, the filter does not do such a great job because it doesn't really remove the noise, but instead it correlates it. For this type of salt and pepper noise, another filter referred to as median filter, it's a nonlinear filter, is doing a considerably better job than the low-pass filter we used before. So on the left you see the same image that I showed in the previous slide, and on the right the result of processing the image on the left with a 3x3 median filter. Clearly in this case the salt and pepper noise is greatly removed, and this is a considerably improved quality image. We'll cover all these things in much more detail when we talk about image enhancement. So we reached the end of week 2. During this week we learned some fundamental concepts for 2D signals and systems in the 2D spatial domain. A crash course in 2D system theory, you might say. The concepts we discussed in 2D are reduced to one dimension or extended to multidimensional signals and systems in a rather straightforward way. So we learned, for example, what is a linear and spatially invariant system. We also learned that complex exponentials, sines and cosines, go through such systems without changing their frequency. We will actually see next week that these complex exponentials are the building blocks of any signal. We also learned that 2D LSI systems can be uniquely characterized by a 2-dimensional signal, which is called the impulse response of the system, and it is indeed the response of the system to an impulse. This quantity can typically be measured. You can take a photograph with your camera of a page which is black everywhere and only has a white spot in the middle. This signal, the impulse response, is all we need to fully describe the system. A very powerful signal and a very compact description of the LSI system. With the knowledge of the impulse response of the systems, we can then find the output of the system for any input by simply convolving the input image with the impulse response of the system. What we have covered so far is extendable to dimensions larger than 2, so this is in a sense a mini introduction to multidimensional digital signal processing. I expect that you'll feel very content now when you pick up a book or an article on image processing and feel very comfortable with its content. What we will do next week is to take what we've learned this week to the frequency domain. It is worth it because, if nothing else, in finding now the output of an LSI system, instead of convolving two signals, we can instead multiply their spectra, a much simpler operation. So, I'll see you next week in the frequency domain.